So when industry embraced virtualization about 15 years ago, there were many concerns and issues that needed to get addressed. Things like security, stability, isolation, you can take your pick. And I would like to think that over the years, most of these topics got to a satisfactory resolution. There is one issue, though, that I find never got properly resolved. And as you might have guessed based on the topic today, that is storage performance. A lot of people think that because storage devices go faster and faster and faster, that's not a problem anymore. And it's actually quite the contrary. As storage devices get faster, as you heard from Jennifer earlier, the time you spend on the CPU becomes more noticeable and you need to be more efficient there. And so it happens that to address things like security, isolation, fairness, et cetera, there is more CPU work to be done when you're virtualizing storage. So today we're going to be talking about Nutanix's very own Acropolis hypervisor, which is a hypervisor based on QEMU and KVM, and the work we've been done to refactor the storage data path in order to meet these changes in storage technologies, right? We went from mechanical hard drives to SSDs. We put SSDs on top of PCIe cards. Then we've got 3D XPoint. I guess I should thank the Optane team for making our life very difficult. And that's a joke. And we're later going to talk about how we're planning on using SPDK. We've been playing with a lot of prototypes, and I have lots of exciting numbers to show you, and how that's going to help virtualize the workloads. So there's a little disclaimer for you to read. I guess the topic at hand is don't buy anything from Nutanix based on what you see here today. There's a lot of forward-looking statements here. Certainly don't hold me liable for anything. I'm going to kick it off by talking a little bit about storage performance and virtualization. I understand we have loads of storage performance experts here in the room today, but perhaps you didn't really think of this in terms of virtual machines. And we're going to try to be very scientific about that. Then I'm going to take you through the storage stack on AHV, and finally talk about the SPDK integration. So what is the first thing you do when you're evaluating a hypervisor, and perhaps evaluating anything? You take a baseline, and then you try to get as good as an apples-to-apples comparison you can, and you measure that again in your new configuration, right? And what better tool for that than DD? And you control the first stone if you have never used DD for measuring throughput. I can see people laughing. It's obviously not good, and hopefully after this talk, if anyone you talk to that still asks you about, oh, what DD says, you can point them to these slides. You can think that in terms of baseline, someone could go there and throw some sort of DD parameters and measure throughput and find that their bare metal environment does 500 megabytes a second. And then they would take as much of a similar software configuration they can from their bare metal environment, put it on top of a virtual machine and measure again. And if they find that the performance went down by half to 250 megabytes a second, that's one of those stable flip moments. And you would come with all sorts of theories and explanations for that. Perhaps your hypervisor overhead is 50%. Perhaps your hypervisor just cannot go faster than 250 megabytes a second. Or maybe you cannot max out your storage, whatever that means, and we're going to talk about that. And I started to wonder which one of these were correct. And as it turns out, all of these statements are actually incomplete. They're not wrong, but they are incomplete. And I noticed that from a previous life when I worked for another company developing another storage data path for hypervisors, where people could use this hypervisor wherever they wanted. Any sort of CPU configuration, with any sort of storage configuration they wanted. So they could use that with local mechanical drives, RAIDs, SSDs, NVMe's, perhaps fiber channel, perhaps SANs or NASs. And some of our customers would say, I don't see any performance overhead. I have the same performance I had when I was on bare metal. But other people would say, no, I have a performance hit, and sometimes it's quite big. It was more than 50%. It could be a lot more. Quite funny, some people actually said it got faster. We're not going to be talking about that today, but it can happen that hypervisors can help your workload to run faster. We can talk about that over coffee later if you want. It's a funny one. So how do we actually find out what's going on? If you find an increasingly higher number of baby memes, it's because I just had a baby and I find all of them very cute. So what exactly do we do? How do we figure that out? And we start from the beginning. We take a mechanical drive, and we try to understand what the latency implications of these drives are. And there are many different ways of measuring performance. As you're aware, there are metrics like throughput, IOPS, latency, and you usually want to know how your workload performs according to those metrics based on different ways of pushing the system. So perhaps for measuring IOPS, you want to know small requests with high QDEFs. Perhaps for throughput, you care more about sequential workloads and you care about larger request sizes. Think about measuring how fast a car is. You could be thinking about top speed or acceleration. Still measure how fast the car is. So in this example, what I did was just measuring sequential reads, something very straightforward with QDEF1. So you can think that I issue a read request, when that completes, I issue another one. And then I varied my request size, which you can see on the x-axis in logarithm scale. And I look at the completion latency for those requests, which you can see on the y-scale, also in logarithm scale. And you notice that for smaller requests, from a single sector up to about 8K, the latency really doesn't change that much, which means the time it takes to read a kilobyte is about the same time it takes to read 8 kilobytes, around 50 microseconds in this example. But from that point onwards, when I increase my request size, what happens is the time to complete the request doubles. And if you draw a line on that, you actually see that the time to complete is actually doubling to a point where a 2 megabyte request in the corner there, it takes, I think, about 20 milliseconds. Right? That's a lot of difference in time. And if we think that associated with this latency, there is some CPU work being done, but even when you move to a virtual machine, the CPU time doesn't increase that much proportionally to the request size. What happens is, as the time to complete the request on the storage device grows, the overhead you have on the CPU becomes less important, less meaningful. Right? You can think that if you were comparing a 5 microsecond CPU time to process a request on a bare metal environment, and 4 times that, 20 microseconds, to complete something on a virtual machine, when your request is taking 10, 20 milliseconds to complete, who cares? But when it takes 50 microseconds, you care. And you can see that by looking at throughput instead of latency. Now I have a different graph, it's the same data, but on the y-axis, I have a linear scale and I'm measuring the throughput of the drive, which goes up to about 115 megabytes a second. So there is this kind of S-shaped curve, which flattens out at the top, and that is what I like to call my storage is maxed out. You can throw a more optimal workload at it, but you're not going to get any better performance out of your drive. And that's exactly because after 16K, when you request 32K, it takes twice the time, so your throughput doesn't increase. Now, what happens from a virtual machine? Can you guess what the shape of the graph looks like? And you find that because of this small but still measurable CPU overhead, for small request sizes, your performance is much lower. So if you look there at 4K, for example, we have about 40 megabytes a second in a VM and maybe 70 on bare metal. That's quite a measurable overhead. But if your workload does requests of 16K or more, you don't see any impact. So that's all fine. I think perhaps this graph is important because for the first time you can actually answer that question I posed earlier. Why sometimes you measure an overhead and other times you don't? And it's largely to do with the workload. Also with the way you virtualize the storage, as we're going to see going forwards. So let's get a more interesting drive. Instead of a mechanical drive, let's look at an Optane drive with 3D cross-point media. So the first thing you notice is that by doing the same workload, which is just varying the request size and doing sequential reads with QDEF1, we're actually not maxing out this drive. You see that this line is not going over my actual plotted series. I actually have a colleague that likes taking a ruler and putting it on his display to measure these things, or any other sort of straight piece of paper, and it says, look, it's a straight. Yeah. And that's a valid thing to do, I guess. Now, if we look at the throughput, first we notice that the scale is very different. We're no longer talking about dozens, perhaps 100 megabytes a second, but we're talking about hundreds of megabytes a second. We can see that this S-curve didn't really flat out at the top, right? And then that suggests that this drive could potentially go faster. Suggests. You could also look at the tech spec for the drive and see that it's supposed to be faster than that. And what I did to figure out how this drive could potentially go faster is picking another CPU and throwing more work at it. So now we have QDEF1 for each one of my threads that are issuing I/O running on separate CPUs. And now we have that curve. And you would find that if you keep throwing, this is obviously a kernel-based data path, if you keep throwing more threads and more work at this drive, this would form a sort of a gradient going left, and you'd probably reach that peak of 2.7 gigabytes a second with slightly smaller requests. Definitely not as low as 4K, but probably smaller than that. And what do you think happens with a VM now? Well, what happens if I repeat this experiment in my VM? And now things get interesting, because now we're talking about gigabytes a second of throughput. And you would find that one CPU from your VM doesn't go anywhere near maxing out this drive. And it will now depend on your hypervisor's ability of taking all of this data, for example, 2 outstanding requests of a megabyte each, and passing that to your storage. And perhaps some hypervisors out there won't do that. In this example, where I'm using QEMU 2.6 with Frodo SCSI, it does do that. And if I issue a second CPU inside the VM doing I/O, then I do get to the max of that drive. But you see how there's still a reasonable measurable overhead to now request is up to perhaps 64K. On 64K with 2 CPUs in the VM, I'm doing about 1.5 gigabytes a second. And on bare metal, I was doing 2.7. That's quite a dent on your performance, right? So this is talking about throughput. There is actually another metric which is much harder to virtualize, which is when you actually have to do a lot of I/O with smaller requests. You can guess that just by seeing that with small requests, we never meet the bare metal performance. And that is IOPS. So if we keep this drive, but we go on bare metal now, and we try to just bump the QDEF, so what you have on the x-axis is now the effective QDEF, and which is essentially how many requests I'm throwing at any one time to the drive. And on the y-axis, you have your IOPS rating, thousands of operations per second. You see that from bare metal with 1 CPU, you get slightly over 200,000 IOPS. And this would depend largely on the OS you're using, on the CPU configuration you have, on your P states, et cetera, how well your CPU can turbo. It's really down to the performance of the core that's issuing that I/O. We know that this drive should do about 600,000 IOPS, so we are at 1/3 of the performance of the drive here. So by throwing another CPU at it, we see the performance going up. And by throwing a 3rd CPU at it, it goes up a bit more. I even threw a 4th CPU at it, and it goes all the way to the top. You may see that the data points is skipping a little bit, because we're now, when we have 4 CPUs doing I/O, you have effective QDEF of 4 straight away, because each CPU is doing 1 I/O at a drive at a time, right? So the important thing is the shape of the curve. And you would find that if you look at a normal NAND-based NVMe drive, this curve looks a lot more curved. And with Optane drives, you just get really fast IOPS with a very small QDEF. What do you think happens with your VM now? So again, it will largely depend on your hypervisor at this point. That same configuration I had before, still QEMU 2.6 with Frodo SCSI, which is what we have been using on AHV. I didn't mention that. You see that the performance of CPU1 compared to the performance of CPU1 on bare metal perhaps is not that bad. But if I throw 2, 3, 4 CPUs from the VM, it doesn't really scale. And now that's a problem. Now we find a customer that paid top dollar for a drive that can do 600,000 IOPS, and you virtualize that workload, and that workload doesn't go faster to what looks like 250,000 IOPS, no matter how much I/O you throw on top of it. And that raises questions. I mean, that's usually when you get a ticket down in the engineering department and say, can you fix that for us? And if we break down and look at this hypervisor configuration, see what's really going on, what you see on the top there is the virtual machine. So there's some storage workload running in user space that talks to some part of virtualized driver, in this example, Frodo SCSI. And then you have some virtual hardware layer where your Frodo SCSI controller is. So as far as the VM is concerned, this is a real PCI device, which has talks Frodo SCSI. Right? So underneath that controller, you can have a number of targets and LUNs, which represents your virtual disks. And all of that is handled by a single QEMU thread in user space on the host side. And that QEMU thread is then talking to the block layer, talking to your storage driver, and talking to your storage device. Now, the problem you have on this particular configuration is that to drive lots of IOPS, you need more CPU power. Unless you're using SPDK, but I'm going to get there. And this is a single thread on the QEMU side handling all that work. And you're bottlenecking on that thread. That thread gets to 100% of CPU utilization, and all it's doing is taking I/O from the VM and throwing it at the drive, and it's going to check on the drive already completed most of it. You pass it back to the VM, you pick the next batch you put in, and you're just doing that, and you can't keep up with the speed of the drive. Now, you will notice that adding more virtual disks, or perhaps even adding another controller, is not going to help. And there's been people trying to solve this problem in QEMU specifically. I'm going to talk a little bit more about that later. Before I do that, I want to talk about different hypervisors. So if you look at XenServer, for example, XenServer has a process on the hypervisor side, or the DOM0 side, called tap disk. And each tap disk is responsible for a single virtual disk on your VM. So it's a block device on the VM that attaches itself directly on the block layer with this power virtualized Xen driver. Now, there's different considerations to make here. Firstly, tap disk is actually a lot more CPU hungry than a QEMU driving for the SCSI. And secondly, tap disk can't really cope with a lot of outstanding data for each drive. I'm not sure if that changed recently. Last time I checked was a few years ago when I was working on it. And you could do a maximum of 11 requests of 44K each, or 44 requests. It's something weird like that, some weird number, which had to do with the format of the ring, some limitation in the format of the ring. So people found that if you want a better performance, you throw more disks at your virtual machine. But that's not really the way you want to scale. Now, there are other hypervisors that make this recommendation too. I'm not going to name anything or anyone. But they say add another controller, because then we get another thread on the host side to handle the traffic of that controller. And the problem of that is if you think about a big VM, I don't know, 60, 120 something odd CPUs or vCPUs running some big database server, do you really want to have to add 100 disks to the VM? How does that even work? You have 100 vCPUs doing I/O over parts of different virtual disks. You create some sort of software RAID maybe inside your VM. That's not how you want to work. How do you do multi-queue with that, for example? And that's not a solution, right? So in this particular model, to scale, you need to add more virtual disks, and the amount of CPU consumption on your host is going to be crazy. So that's a funny topic, because people like to say, oh, SPDK burns the CPU. Do you have any idea how much CPU you need to burn here to get to anywhere near the same level of IOPS, or even on the QEMU model? So let me start talking to you about AHV. So AHV up to version 5.1, we had a very similar model to what I was explaining before for the SCSI. Except that our backend is iSCSI. So instead of talking to the block layer on the host side, we talk to the network layer, and then we talk via iSCSI to another virtual machine that sits on the same host. So I said I was going to mention how QEMU tried to fix this problem, and QEMU has been working, the QEMU community has been working on something called data plane, which is a means to have more threads inside QEMU handling storage traffic. Last time I checked, some point last year, data plane was still under development, and they were still struggling to get it to work properly, and that's been the same story for the last 3 years or so. QEMU is really complicated, and solving this problem inside of QEMU is really hard. And you heard Jim talking about vhost. What we did to address this problem is create a mechanism to extract the storage data path out of QEMU. And that's what vhost means. It means offload virtio to the host. We specifically worked on something called vhost user SCSI, which you see here in this slide, which starts on Nutanix AHV 5.5 onwards. And using vhost user SCSI, we offload the virtio SCSI data path to a separate process, which we call Frodo. So that's our own component to do that. Frodo stands for facsimile relay of data path operations. You can also think that it's the guy that carries the rings, the I/O rings in this example. And it is really facsimile, because what we do is we consume the SCSI commands from the guest, we put an iSCSI header, and we ship it off the network. So Frodo does very little work. It's very efficient. The software is very, very lean. And on top of that, we expose a multi-queue controller to the guest, which we can truly benefit from, because we can make Frodo multi-threaded. Because of the way we handle iSCSI, we can actually do that, and have completely separate data paths from different VQs in the guest. So a quick dirty comparison, on our QEMU on 5.1 on top of our stack, it was doing about 80,000 IOPS on 4K random reads before maxing out on that single CPU thread. With Frodo, we can do about 160,000 IOPS per thread. And if the stars align, you can do a lot more. It's not a limitation for itself. It has to do more with the iSCSI part of the work. You also heard Jim talking about how iSCSI still has to go through the kernel, right? Even though we're pushing for a full user space stack here. So on the multi-queue side, if you're not familiar with multi-queue, the way this works as far as the guest is concerned is we present a Verde iSCSI controller with one VQ for each one of the vCPUs of that guest. And that's quite interesting, because if you think of a real NVMe controller, you have maybe 30 VQs. I actually haven't checked what's the latest on that. But the spec allows for a lot more, but vendors don't really do that. With virtualization, you can expose as many queues as you want. And I think our max number is in the 1,000 or so VQs ballpark. And from the guest point of view, if the guest has multi-queue enabled, specifically for SCSI, what you would do is create a software queue for each one of its block devices to match those hardware or virtual hardware request queues you were seeing on the bottom layer there. So if you have some work running on the CPU 1, there on the far left, and that does I/O on the drive on the left, it will use the request queue 1. And you're guaranteed that no one else is going to be using request queue 1 on any other drives of this VM, because that's reserved for CPU 1, and CPU 1 can only do one thing at a time. So you can have a lock-free data path all the way to the request queue in the controller. And Frodo, on the other hand, can consume that lock-free as well and ship it off the iSCSI backend. Not only this allows for a lock-free data path, but it creates a very interesting scalability point, which is we are scaling a VM with the size of vCPUs it has, and not on the size of disks or controllers it has, which is really what you want. Now, if you have a VM that has 64, 128 vCPUs, and you put a big database there, each one of those vCPUs can do I/O lock-free. They don't have to content lock across perhaps NUMA nodes, and we know how bad that gets. And we are creating a means of scaling the VM based on the size of VM, and not necessarily the storage configuration. On top of that, because we have more VQs, we get to support more outstanding requests. Each VQ, by definition, on the Verde spec does 128 requests. You can outstanding at any one time. You can tweak that, but it's a bit tricky. And we don't have to do that. We just, hey, your VM needs to do more work. You probably need more vCPUs anyway. And that's how it scales. Now, I wanted to talk a little bit about that part of the iSCSI bit on the network layer, because we're talking about very fast storage devices. And the way this works on Nutanix today is we go through the network stack on the hypervisor, and you talk to a local VM, which is a special VM. We run one of those per node, called the CVM. And that goes through Verde.net to a component which we call Stargate. It's our virtual storage controller. And Stargate then talks to the NVMe drive. Now, we've been looking at using SPDK inside the CVM so that Stargate can talk to the NVMe drive directly. NVMe, in this case, that drive is passed through to the CVM with a PCI pass-through. But we thought we really need to cut this data path short. So the way we've been playing with this now is actually bringing that NVMe drive back to the host and figuring out how to get Frodo to talk to that drive locally to shorten the data path and reduce the amount of CPU work we have to do. Now, one way of doing that is going through the block layer in the NVMe driver and talking to the drive, or not. Obviously, we're not going to do that, otherwise we wouldn't be here today. We're looking at hooking up Frodo with SPDK. So the idea is Frodo can then talk directly to that drive from user space and make the storage path really, really short. We already mentioned how Frodo is lean in terms of the work it has to do. SPDK helps us a lot because we can just parse perhaps reads and writes, and anything else. We can still have a shadow volume if we want on Stargate to respond to more complicated SCSI commands. But most likely, we're going to implement a few SCSI commands that we need in order to make this stack complete. And in terms of the data organization, we're planning on an initial offering for RF1. So there are workloads that already take care of replicating the data across a cluster. I don't know how familiar you are with Nutanix, but the whole idea behind hyperconvergence is you have a bunch of clusters, as many as you want, and your data is accessible from wherever you are in the cluster. So your data is replicated in specific places. You have at least a replication factor of 2 or RF2. And if your VM starts running somewhere, then due to data locality, the data follows your workload. Right? So it works really well. So for an RF1 mode, we would have the data only in one drive to one node. We would probably pin that VM now initially and then figure out if you want to support migrating that VM around. We could do that. We can copy the data, for example, when you want to migrate. One of our early prototypes actually copied the data back to Stargate And then you have a full feature VM which can move around, do your upgrades, etc. When your VM settles somewhere, it pulls the data back to NVMe, folds the data back in. And for the data organization on disk, we've been looking at blobfs as an option. Now, there is one point here, which is Frodo can talk to the NVMe drive, SPDK style, so we can submit the drives and then spin on the drive and wait for it to complete. But it can also do more. We've written a thread model called Pulsar, a thread pool model, which is similar to an SPDK reactor. And we can do more than just spin on the NVMe drives. We can actually spin on the VMs as well. So we eliminate the need for the VM to kick us when it has some work to be done. We can just keep constantly looking at the VQs. We burn one CPU on the host side, and we can do quite a significant amount of I/O. And the downside is we still need to figure out we still need to interrupt the guests, right? And when you complete the request, we still need to tell the guest we've done something. And that's where it gets nice, because the guest can also use SPDK. SPDK already supports Frodo SCSI as a poll mode driver. And if you do that, then the VMs don't have to get interrupted. It can disable notifications all across the stack. So the VM puts the request somewhere in the memory, and Frodo immediately sees it, picks it up, passes on to the drive, keep looking at the drive. As soon as it completes, it puts a completion on the guest, and the guest immediately sees it because it was looking at that. Oh my God, I'm burning 2 CPUs. You've seen my initial graphs. I'll show you some more now. The amount of CPU you're saving by doing this is insane. I have a graph that's a bit tricky to read. It's a bit confusing, but I'll walk you through it. What we have on that purple line on the top was my performance on the host on bare metal using 4 threads doing I/O, which got me to that 600,000 IOPS mark. On the lower 2 green lines, you have the performance of 1 CPU and the comparable performance with 4 CPUs from a VM, on top of the Frodo SCSI, on top of a normal QEMU 2.6 doing I/O to a local NVMe drive. Now, how does it look like when we try the same workload on top of this Frodo that does SPDK? And with 1 CPU in the guest, you can see that we get to that. If you remember how the 1 CPU looked like in the host, that's very similar. And what happened here is we actually moved this bottleneck to the VM. The VM is actually struggling to put more I/O in flight. Frodo still has plenty of capacity. And what we did is we went on and started a 2nd thread inside the VM, and it scaled really well. And we started a 3rd, and it kept on scaling. This is a bottleneck inside the guest trying to put I/O on the VQs and then getting interrupted for the completions. It's nothing to do with the hypervisor anymore. It's the guest that's inefficient. And then finally 4 CPUs, and we got to a point where we're really close to the top there. If we start a 5th CPU, it actually gets to the 600,000 IOPS mark. Right? So we can actually max out this drive now, which is something, as far as I know, no other hypervisor is doing at the moment, just by improving the storage data path on the hypervisor side. Now, if you wonder what happens when we actually try to put the poll mode driver in the VM, that gets really interesting. That's the orange line there. 1 CPU in the guest doing I/O directly on the controller, which is this Frodo SPDK-enabled controller. You actually max out the drive much faster than what you did on bare metal with 4 physical CPUs doing I/O. That's how efficient SPDK can be. If you want to have some other data later, that shows that with 4 Optane drives, right, on the same box. And you essentially need 1 CPU on either end to go to crazy numbers. So what's next? We have one challenge to fix before we can make this a really, really interesting offering, which is to have 1 Frodo managing multiple virtual machines. The challenges with, so this is obviously a way of spinning more efficiently because I can have 1 CPU on my hypervisor dedicated at handling all the virtual machines in the node. It also makes it a lot easier to manage the single NVMe drive. I don't need several processes, and that gets complicated. But there are some challenges involved in that. For example, if this Frodo crashes or goes down for whatever reason, then all my VMs on that host lose the storage. So I need to figure out of making that restartable and picking up the data path where it left. Another problem is perhaps to do with memory fragmentation. So every time you start one of those virtual machines, QEMU offload the data path to Frodo. He actually tells where all the guest physical memory for the virtual machine is. And Frodo needs to map that in its own VMA. And this comes in regions, especially if the VM had memory that got hot plugged to it. Then a VM goes down and you have these holes in your VMA, and you want to power another VM, perhaps it's bigger, you need to find more VMA space. And you'd be surprised to find that it's not that hard to exhaust your VMA space or end up with holes everywhere. And you can't fit more VMs in. So there are some challenges to be solved there. And the whole idea of spinning more efficiently is quite exciting, that you can dedicate one CPU and you don't have to have kicks from any VMs anymore. So to summarize that and discuss what we're doing next, we have, we've talked, I'm the third person here today talking about that, but the faster the storage device, the more important it is. The more important is the CPU work you're doing. You want your CPU to be linear, you want your software to be linear, you want the CPU work to be more efficient. You also, that means it's harder to virtualize, right? Because again, you need to take care of security, isolation, etc. So what you need to do is be very careful in the way you design your storage data path. And this is not limited to multi-queue, but multi-queue is important because maybe not all of your guests can work with SPDK straight away. And it also requires careful design in the way that you allow for scalability. So how do I guarantee my VMs can put as much data in flight as he wants? How do I guarantee they can put large amount of data and large amounts of requests? And probably in a zero copy kind of way, otherwise you find that your hypervisor CPU consumption is really, really high if you need to copy megabytes of data every time you're processing requests around. That takes us to this idea of a user space only stack. I believe that vhost user is perhaps the first way that we can take a data path from QEMU, or in this particular case, and actually make a user space only data path. So you can have a user space process that can directly access VM memory and can directly talk to an NVMe device with SPDK without ever having to go into the kernel. And if your VM is using SPDK as well, same thing. Don't ever go into the kernel inside a VM. And as far as SPDK integration goes, we have to, sure, this RF1 offering is really interesting. It's also interesting from, as I said earlier, from a point of view of space efficiency, but of performance as well. But we have to figure out how we're going to start using this for replication. So can we still work from the host and replicate this to other NVMe drives, and then still have our software intelligence inside Stargate doing more interesting things like what it does today for the duplication, compression. He offers access to storage for other means which are not directly for virtual machines. So we have offerings where you can access Stargate from NFS or iSCSI directly. It works as a full-fledged storage controller. So we need to think about how to do that and perhaps use NVMe over Fabrics for that in the near future. I'm having conflicting times here. I believe I've reached my 40 minutes mark, which leaves 5 minutes for questions. Clock says I still have about 12. So I don't know, if you have any questions, I'll just take them now. Back there.
The graph that you showed, which had the guest SPDK giving better performance, how do you explain that? Or what was the reason as far as you could tell?
You were talking about, sorry, when I have my laptop with me, it's easier to flick through this. You were talking about that orange line there. Right. So what's happening on the orange line on the top is that if you think of the diagram I had before, and I want to keep this graph here for a minute, but think that there is an application inside of the guest. In this particular example, it was SPDK's perf. It's talking directly to the Frodo iSCSI controller. So basically, it looked at a PCI device, which got handled over to user space, and it mapped all the VQs, et cetera, in its own memory. So all it has to do to issue a request is fill in a few data structure entries. Frodo and specifically Frodo iSCSI data structures entries, which is the descriptor table and the little ring. And as soon as he writes the index to the ring, at the very moment, Frodo on the hypervisor side will read that ring. That's all Frodo is doing, is looking at the index saying, do you have anything for me? As soon as it sees that index, it can go into the guest memory straight away, which is already mapped, and consume those pointers that says this is a read or a write request going here or there, and immediately handle that over to the NVMe device using SPDK. As soon as it completes, it goes into another data structure with the guest, which is a completion ring, and just writes an index there. The guest itself was spinning on that ring, and it immediately sees the completion and consumes that. So people underestimate the cost of kicking, and that is when one of these processes is sleeping and you filled in the data structure, you have to send a notification down to the other side, either notify the device or interrupt the guest up. This is really expensive. Not only all the switches that cost. For example, when a guest kicks, there is even a VM exit involved, which means your physical CPU goes out of VM mode and the control gets handled back to the hypervisor, which then make an internal event FD mechanism available so that some call inside hypervisor, specifically in Frodo, which is selecting or pulling on a file descriptor, will say, oh, I have to read something. And then it reads that notification and it knows it has work to do. So all of that goes away immediately. And that has largely to do with the amount of latency you're saving here. Not only that, but the stack inside the guest is also so much more efficient because the code is all in SPDK. All the SCSI stuff that you need to do for AOSCSI is all there. You don't have to go into the kernel, go through a common block layer, which is perhaps serving requests to all sorts of other devices as well, go through all the common data structures, and then go to the SCSI mid layer, and then finally to over the AOSCSI driver. You're also saving all of that work. So that's why this is so much faster. And there's another thing, which we were talking about earlier, but perfs is incredibly optimized for this. To the point, I don't know if Ben is going to be talking about that later, but to the point where they actually, or Daniel, that they actually look at how perf is executing, and they fix little assembly black magic things that I don't really understand to make that software faster. Right? And I think that we're having to learn so we can do that in Frodo as well. Does that answer? Thanks. More questions? Someone walking with a microphone.
Thank you. So I have a question is, so you make the guest had a spinning thread trying to pull in the completion event, right? So how about the CPU consumption for changing to that?
Right. So the question is regarding with CPU consumption in the guest when the guest is spinning on completion rings. As you can see from the light blue line, the one that goes to 600,000 IOPS, if you wanted to get to that level of performance from the guest, your guest would actually have to be using 4 CPUs, or actually it's 5 CPUs to get to that performance, 5 CPUs. And that is, again, to do with the cost associated of imagine that there is a lot of software work that needs to happen for your workload, or even a synthetic workload in the guest, to go to the kernel, to actually populate the data structures, and then ring a doorbell on the device. So when he does that, for that particular vert queue, we have multi-queue here, right? Particular vert queue, that means the physical CPU goes out of virtual machine context, the control gets handled back to KVM, KVM delivers a notification to hypervisor, and then resumes the execution of the VM. Depending on the guest kernel you're using, your kernel may actually be polling already. So I think from 4.10 onwards or so, the kernel started to do various different types of polling. Most recently, I think there is this hybrid idea where you actually know for a certain request size how long it's expected to take, and then you set up a timer and you start spinning just before that time, trying to keep your CPU utilization low. But the fact at hand is that there is so much more work to do with the whole kernel data path that to get to 600,000 IOPS, you actually need a lot more CPU than you needed with just one. And the challenge there, I think, is for workloads to actually use SPDK. So, which is out of our hands, and that's why we're doing the work on the hypervisor anyway. But you can think that if you're running a database application, the database needs to own the whole controller. So you need your database software to work with SPDK to submit I/O to that controller. The good thing is that if they're using SPDK already, hopefully it doesn't matter if they're talking to an NVMe driver over the AOSCSI drive. Maybe it does, but maybe it's a smaller effort to get that to work. So I truly believe that an increasingly larger number of workloads will start looking into these alternatives. They have been for a while, and you're sooner going to have more and more applications that require this kind of storage performance linked with SPDK, and then trademark. It just works.
Hi, I have a question about the yellow and purple lines. In particular, how would the purple line would be on the host?
The purple?
If you use SPDK also on the host without virtualization.
Good question.
And another question is how would those two lines compare if instead of if I read it right, is a 3D cross-point disk, if you would use an Optane disk?
Right. This is an Optane drive.
Oh, okay. Sorry.
Yeah. So the only difference between the Optane, or the only difference between an Optane drive and a normal NAND-based drive is that that curve, instead of looking that sharp going up, it's going to be more like this one's here. They're going to look more smooth going forward. So you need more QDAP to get to that level of IOPS. That's the main difference. Now, your first question was to do with the purple line was the host doing I/O with 4 CPUs using libIO. And that's obviously unfair because on the orange line, I'm using a full SPDK stack. So obviously, it's not a fair comparison. And then that's a good point you raised. I actually think I have that graph, as a matter of fact. But unfortunately, I can't jump straight to it with this remote. But I can probably get that. That one. So the colors here are completely mixed up. This is from a different presentation. I apologize. What you have here this is also a different CPU configuration, which means the numbers are slightly different. But on the black line here, that's the VM doing I/O with SPDK on top of an SPDK-enabled Frodo. The orange line on the top is perf running directly on the host without any virtualization overhead. So in both cases, in the orange case, you only have one CPU on the host being used, which is perf. And on the black case, you have a perf in the VM and Frodo using SPDK. So there is still an overhead, but you can see how much smaller that is if we compare to those graphs I was showing earlier, both in terms of throughput and IOPS for the kernel data path, right? Even if at a QDEF of 4 or 5, just around here, the difference exists, but it's not that meaningful. It is, but perhaps at QDEF 4, seriously, right? At QDEF 5 or 6, you're pretty much maxing out your device already. I think that's pretty good. But as I said, that's only until the next technology of drives come up. I'll have to come back here and talk to you about what's happening there. I don't know how we're doing on time. I think we're good. Thank you very much. We'll see you around the coffee area.